Welcome everybody. Welcome to our lunchtime webinar today. Today's on a really important and really interesting subject, which is how we're going to balance the embodied carbon that goes into doing our building projects with the operational savings that we can make from those projects. How do we get that right balance for our church buildings? Before we dive in, I always start with my preview of upcoming attractions. So we've got one more webinar left this side of Christmas, which is the really interesting one being led by Toby Curtis on conservation pitfalls and how to avoid them en route to net zero carbon. A really good guide to the things that can go wrong and how to avoid those things going wrong. And then looking into next year, we're running this session again in February and in April. And I've also got Eco Church dates in the diary for our getting started, our gaining momentum, and our net zero carbon Eco Church sessions. You'll notice that that third one, the net zero one, we're running in January because the date it was meant to run a few weeks ago was cancelled due to illness. So we're catching up with ourselves in January. There will be some more webinars that I'll be getting scheduled and publicised shortly, but these are the ones I've got in the diary so far for next year. As ever, we'll be using the Q&A today rather than the chat for your questions. So if you can move your mouse about, find the Q&A, that's where you can pop your questions in. You can also see other people's questions and you can put a thumbs up next to the questions that are of most interest. And when Douglas and Nigel have finished speaking, then we'll turn to those questions and we'll start with the ones at the top. After the webinar, I'll be sending you around the slides and any links that are shared in the chat, and also a link through to our short feedback form. And I record these sessions and I share them via our website on the same page where you book to come onto the webinars. Right, let's go on to the main event. So we've got two really well-informed speakers for you today. We've got Nigel Griffiths, who's the policy advisor for the STBA, and we've got Douglas Kent, who's the technical and research director at SPAB. And they're so well informed on this subject, and we'll take you through the basics and a worked example. And if you haven't come across me by now, I'm Catherine Ross and I'm part of the Church of England's Environment Programme, and I'm based in our Cathedral and Church Buildings division. Right, let me stop sharing my screen and hand over to Nigel, who is going to take us away.
Thank you, Catherine, and good afternoon, everyone. Hopefully that should have taken us full screen now.
Yes, it has.
The two Ronnies used to say, in a packed programme tonight, we've got quite a bit to cover. We're really going to get some basics, a basic understanding of the subject, and where you can get actual information on embodied carbon. And then we've got to do a little bit of work on savings, so that ultimately those can be compared with the embodied carbon. So we'll take you through that whole process during the course of this, the next 40 minutes, basically. So that's what we're going to be looking at. And we're going to start off with an introduction. What is embodied carbon? Well, basically, it's the carbon emitted in the production, transportation, and installation of building materials. It replaces an older term, embodied energy, which had, of course, the advantage of alliteration. But carbon is the kind of language that everybody's speaking at the moment in the kind of the context of climate change and the efforts that people are making to mitigate it. Got to be a little bit careful here. We are not talking about sequestered carbon. Sequestered carbon is good news. Embodied carbon, not always such good news. So sequestered carbon is what really happens when trees grow, and then we take out products from them which are then installed permanently in the built environment. Mainly wood, but also wood waste, such as insulation that's made from wood waste. Some really good products around. Even warm cell, which is insulation that's made from recycled newspaper. That's all sequestered carbon, ways of locking up carbon in the built environment. That's not what we're talking about today. A building material could have both sequestered carbon and emitted carbon, because it takes a certain amount of carbon to produce timber products. But the real villains in this piece are things like concrete and steel and so forth. They really have much higher embodied energy and thus embodied carbon. Why does it matter? Well, in terms of new build life cycle emissions, embodied carbon accounts for up to 50%. Or if you look at the entire life cycle of the building in terms of building it, running it, and then ultimately demolishing it and recycling it. But the materials that we put into our buildings now cause emissions now. So if you're looking at retrofit, basically what that gives you is a carbon spike. So you might well be intending to save carbon emissions by retrofitting a building to improve its energy performance, as we call it. But actually what you're doing is you're causing a huge amount of carbon emissions now. So that's why embodied carbon matters so much. The other reason it matters in that context is that the carbon intensity of the electricity grid is falling quite rapidly now. Therefore, it gives us a much more nuanced decision in terms of emissions now or emissions in the future, because future emissions, especially as more and more buildings move over to electric forms of heating, the kind of emissions from running them will fall, but the embodied emissions are what they are now. So that gives us the kind of context, if you like. I'm sure you'll be looking at this in other forms of seminars that you're having in this series, but it's worth just reflecting for a moment on what you mean by net zero. Does it just mean that you're getting your fuel supplies from a totally green, 100% green supplier? Does it mean you're offsetting by planting trees in some way, or are you making some sort of attempt to offset it on the building itself, which is never an optimal solution, really, because you get a terrible mismatch between supply and demand. But in this context, you just need to think a bit carefully about what we mean by net zero. The policy context for this whole thing is changing very rapidly. And the Climate Heritage Network presented at COP26, and their kind of headline was that building reuse is climate action. So basically, especially looking at it from an American perspective, because quite a lot of the leads on the Climate Heritage Network came from the United States, where buildings are routinely demolished much more often than they are reused and upgraded. They were trying to make the case that the carbon embodied in existing buildings means that we should preserve them. Generally speaking, architects are looking much more to LCA in new construction. And just before the heat and building strategy was released in November, Lord Callanan said that, we shall be looking at embodied carbon, but actually there wasn't much mention of it in the heat and building strategy when it actually came out. The Church of England itself, of course, has got its Scope 1 and Scope 2 2030 targets, and has done some very, very useful work, which I'm going to touch on in a moment, is doing some with Historic England, and there's some previous work as well. The London Plan, which was released in March 2021, takes embodied carbon into account, and there is now a campaign, if you like, to introduce a new Part Z to the building regulations. This hasn't got as far as government departments, communities, local government, whatever they're called these days, Department for Levelling Up, but some people would like to see a Part Z of the building regulations which covers embodied carbon. It's on the agenda. When we talk about embodied carbon, we need to understand what the boundaries are, and this is probably one of the most difficult issues about embodied carbon. I mean, do we just mean the carbon that's embodied in making these materials, or are we going to add the actual process of installing them on site? Do we need to get the workforce to site? And that is a Bentley for those of you who've got sharp eyes. Rates have gone up in the building industry. And are we looking at the disposal of waste that's generated on site or generated in the retrofit process? So that is quite a difficult question, defining the boundaries, and different databases use slightly different boundaries. So we also need to take into account maintenance, of course. Some materials, once installed, need maintenance every decade, 2 decades, or in the case of, let's say, a lime-built wall, perhaps every 100 years needs to be repointed. So there are certain standards which define these boundaries for you according to which you select. There's European standards. There's the environmental product declarations themselves, which again, we'll come back to. They're very useful. And there's even a public standard, PAS 2080, for carbon management in infrastructure. So all these things are important. When you're looking at building materials and the building processes, you've got basically construction, operation, maintenance, and demolition. And depending on where you draw the line in terms of the boundaries, you can either get what we call cradle to gate, which means the delivery of those materials to the site gate where they're to be installed. Cradle to grave means once the materials have actually been taken out and taken to the tip. What we hope would happen would be that materials would be recycled and reused, either in their existing form or in a new form, and that we call cradle to cradle. So those kind of life cycle analysis terms become relevant to the embodied carbon discussion. While this seminar will very definitely, of course, focus on embodied carbon, we do just need to be aware that you can get too focused on it and miss the other impacts of construction materials. I'm not going to dwell on it, but water use is important, and we're starting to get a handle on this when we talk about food production. Resource scarcity, of course, is important, and PV panels are one culprit in this. There are some rare minerals used there, and pollution, of course, is another one. And the pollution, it may not occur on site in the UK. It could occur a long distance away where the materials are actually produced. So embodied carbon is not the only thing that matters in terms of construction materials. There is a terminology in which this discussion takes place, and all the metrics themselves are based on what we call carbon dioxide equivalents. Now, there are many different greenhouse gases, but the convention is to multiply them by whatever factor is needed to get an equivalence in terms of carbon dioxide. So we talk about CO2e, CO2 equivalent. However, that's not the only issue here. If we are looking at a material which is most easily measured in terms of area, then we talk about kilograms of CO2e per meter squared. Certain materials are quoted in terms of volume, so you're looking at the same metric per meter cubed. And just to confuse things even further, the most common method used for measuring embodied carbon is by weight. So it's kilograms of CO2 per kilogram of material. And that gives you always a bit of a problem in terms of comparing apples with oranges. And you just have to be very careful to check which metric is being used. And if you're comparing two different materials together, or even two different strategies more likely, then I think that gives you some difficult maths to do. Very briefly, in terms of available data, the thing that I think we're going to be going to mostly is the ICE database. It's been around for a long time, but it was re-released in 2019. So it's the inventory of carbon and energy. And this has got data for over 200 materials. It's a very good database, and it's really quite easy to use. And it's a free download, and I'm going to give you the link at the end of this talk. There are some alternatives, come to those in a moment, but the thing to be aware of is that almost all data is gathered for new build purposes. Now, Carrig, some consultants based in Dublin, did a very good study in 2019 for Historic England. It's called Understanding Carbon in the Historic Environment. It's good bedtime reading. Now, there are two key conclusions I just want to highlight. And firstly, they pointed out that very few studies have considered whole life carbon for historic buildings. And of course, many people on this call are going to be responsible for historic buildings. And the historic carbon, of course, A, it was low, and B, it's sunk in the building many, many years ago. The emissions that were created when those materials were manufactured an awfully long time ago and have long ago been soaked up. But they also pointed out that there wasn't a single one-stop shop tool for looking at LCA for refurbishment, and it's refurbishment that we're going to be focusing on, or rather retrofit. In terms of other available data, you can go straight to environmental product declarations, which are themselves used in the ICE database. There are various databases that you can pay for, and for particular materials, you'll find that there is some specialist data available. I've just highlighted two. because concrete and lime both have readily available data from manufacturers. And that can be very important if you're looking at lime repairs on an old building. Why do we need to think in particular about retrofit? Well, the carbon embodied in old buildings, we don't really need to worry about. It's there, it's sunk, it's long ago. And unless you're proposing to demolish a building, I hope none of us are, unless you've got something ghastly from the 1960s, then let's reuse what we've got and improve it. So proposals then come forward for change, for upgrade, for retrofit. And we need therefore to consider why retrofit is a good idea for a particular measure, or a series of measures for a particular building. And remember, of course, that retrofit has other effects. It's not just about saving energy and reducing carbon emissions. There are also heritage impacts, good and bad, from retrofit, and there can be very positive community impacts as well from retrofit. So it's not just a carbon question. And the STBA recently published a paper called From Retrofit to Regeneration, arguing that regeneration is really the approach that we should be using to our built environment, and to be regreening and rebuilding communities and looking at water and drainage and so forth at the same time as looking at retrofit and energy. So if you go into the ICE database for a particular material and you scroll down a few hundred lines, you'll come, for example, to insulation, and you will find within that there are various different materials listed. And in this case, their embodied carbon is quoted per kilogram. So once you get into a particular project, and we'll do a worked example in a moment, the embodied carbon is in terms of kilograms of CO2 per kilogram of material. So that's basically what we're going to be looking for within the ICE database. But that, unfortunately, is not where it ends. That's kind of cradle to gate, if you like, to site gate. But there's also the impact of installation itself. Very, very difficult to put a boundary around this one. You've got to get the workforce to site. There's energy that's used on site. There are site services and so forth. And water that's used on site, and that itself has an energy component. And then there are site services such as scaffolding. If you're insulating the external walls of a building, then you're going to need scaffolding, and that, of course, has an impact of its own. You could add 10% as a rule of thumb. I don't know, the industry doesn't know. We don't have good statistics on this yet. The industry is, well, the subject, if you like, the discipline is a very young one. So make an allowance just to indicate you've thought about it. But you can then come back as better data comes forward and refine that allowance for the impact of installation. I'd like to hand over now to my colleague Douglas Kant from the Society for the Protection of Ancient Buildings to explain why historic church buildings are particularly different in this respect.
Thank you, Nigel. So, special considerations for historic church buildings.
Sorry, Douglas, it went forward then without me asking it to.
Oh, there we are. Great, thank you. There are various special considerations that we need to bear in mind when contemplating measures to improve the energy efficiency of churches if we're to achieve successful outcomes. Three principal ways in which churches typically differ from many other buildings and that have a bearing on how we approach measures to reduce carbon emissions associated with them are, firstly, their built form, including their shape and configuration. Secondly, their historic significance. And then thirdly, their patterns of occupancy. Let's look at each of these three aspects in more detail. So next slide, please, Nigel. Compared to a lot of other buildings, the built form of the typical church is characterized by high ceilings and few internal walls that create an interior with a large internal volume. Churches have frequently been extended with side aisles over the centuries and roofs raised at the same time with clear stories to provide additional light centrally from above. Windows also occupy a large portion of wall area. Next slide, please, Nigel. Our historic churches are often the oldest buildings in villages and towns, steeped in history and with ancient, unusual and fragile fabric. 12,500 of the Church of England's 16,000 churches are listed, so are recognised as being of historic or architectural significance. A building's fabric is the primary source from which knowledge and meaning can be drawn. Materials and construction methods bound up with the fabric of a building illustrate changes in people's ideas, tastes, skills, and the relationship with their locality. Fabric also holds character and beauty. The surfaces, blemishes, and undulations of old buildings speak of the passage of time and of lives lived. Wear and tear add beautiful patination that new work can acquire only through the slow process of aging. The SBB advocates conservative repair, in other words, an approach that guides work to old buildings in a way that doesn't harm their special interest. Such an approach has two main tenets. Firstly, because the SBB sees the value of an old building as lying primarily in its material fabric, it's crucial to retain physical authenticity. This entails keeping and not harming what's generally old in most cases, so the real surviving stained glass, wall paintings, floors, and so forth. Secondly, we need to retain the integrity of the building, so its overall essence or spirit. For example, we should avoid overzealous subdivision of the interior to preserve the open nature of a church, as well as minimise the visual impact of cable routes and other components related to building services. To conserve the authenticity and integrity of an old building, we must have good information about it, carry out work essential only to the building's long-term survival, and use technically compatible methods and materials, particularly those that assist breathability or moisture openness. In other words, absorb, transfer, and release moisture readily from the existing fabric to avoid dampness. And next slide, please. The occupancy pattern of churches varies. So some churches, particularly the more isolated ones, see only occasional use. They include festival churches, which are kept open for church festivals, notably Christmas and Easter, and to celebrate rites of passage such as baptisms, weddings, and funerals. A great deal of churches are in regular but not constant use. This can be weekly, although certainly in my area, it's increasingly fortnightly. And then there are churches, usually the larger ones, in more urban areas that are in constant use and hold more than one service daily. Thanks, Nigel. Over to you again.
Thank you, Douglas. And of course, a building that's in constant use has got a very different rationale for having retrofit measures, and because there's a lot more people to actually heat, so it changes the calculation. Very briefly, just want to touch on methods of estimating savings in use. And the majority of the discussion is really about fabric measures, but when you come to non-fabric measures, and you can fairly easily get a handle on the embodied energy of putting in LED lights. But for actually working out the savings, you can work out the differential in watts from your original lamps to the LEDs and multiply that by hours per day and days per year, and then convert to carbon at the prevailing rate. And of course, this is falling over time. Currently, we think under 0.3 kilograms of CO2 for each kilowatt hour of electricity. Heating systems, again, another kind of non-fabric change that you can make to a building. They themselves do have an embodied carbon component. And usually this is pretty negligible compared to the amount of heat they chuck out. So it's not something you need to worry about. But if it is a building, as Douglas says, in occasional use with a very low heat demand, then the embodied energy of the actual heating system itself starts to become relevant. So worth bearing in mind these two types of non-fabric measures. That said, just want to talk about estimating savings from fabric measures for a moment, and there are basically two methods of establishing both base use and savings. Method number 1, which I do not recommend, is modelling. And that basically puts the dimensions of a building into a model, and U values of all different building fabric, works out heat losses, and then tells you how much energy you're going to need to keep it at a certain temperature. Well, it's a truism that all models are wrong and some models are useful. But of course, in our church buildings, we don't tend to heat them to recognise comfort temperatures in any case. So I always recommend method number 2, which is starting with bills, which will give you an actual number of kilowatt hours used if you look carefully enough on your bill, or you are able to convert from cubic meters of gas to kilowatt hours using the conversion factors supplied. There are still issues with estimated bills and comfort temperatures here, but at least it gives you a more realistic basis for starting to work out savings. So we are using X thousand kilowatt hours per annum of energy to heat this building. What are we going to do to change it, and what realistically will that save us? So using this build method, there are basically 4 steps. You establish your total space heating energy and then convert to carbon. It depends, of course, whether you're gas heated or electrically heated, possibly LPG or even biomass. Of course, with biomass, the emissions are negligible. Then looking at the particular element that you are going to improve, you work out or estimate the proportion of heat losses through that particular estimate. So through element, I beg your pardon, windows, you might say we're losing 15% of our energy through the windows. You then estimate an amount by which the insulation or improved glazing will reduce heat losses through that particular element. And you might say that, okay, if we secondary glaze these windows, we might save 50% of the heat losses through those windows, which would be a good thing. Unfortunately, then you've also got to allow for comfort taking. In other words, you might end up just running the building at a higher temperature. It might have been far too cold to start off with. So you might have gone to all this wonderful effort and embodied energy and embodied carbon to retrofit a building, but actually you find that your energy consumption hasn't fallen at all, and that's because the internal temperatures have gone up. We call that comfort taking. But only when you've multiplied all these 4 figures together can we get to an annual saving. And so if it were secondary glazing on a building using 20,000 kilowatt hours a year, that would be emitting on a gas boiler about 4,000 kilograms of CO2 a year. If we save 15% of that, we might get to a saving of 600 kilograms. Halving that with the retrofit measure might take us down to 300, and then halving it again for the comfort taking might take us down to only 150 kilograms of CO2 saved per annum. And that really is quite a small saving in kind of overall energy terms for what would be quite a significant intervention. I should add, and Catherine would want me to stress, I think, that you're not expected to carry out these calculations. You get some kind of consultant like myself to do it for you. But I wanted you to know how they are done, because it is very important when you start to compare embodied energy savings. Sorry, embodied carbon savings. And again, I'd like to hand back to Douglas to talk a little bit about St Mary the Virgin and the strategies that were carried out there.
Thanks, Nigel. Let's consider a case study then explaining how options to reduce carbon emissions at the Church of St Mary the Virgin at Wendon Samborough in Essex were assessed for the Parochial Church Council, or PCC. The building, as you can see the photo here, is a small medieval church. It's got thick flint walls and limestone and conch or chalk dressings, and roofs covered with plain clay tiles and lead sheet, and the floors are tiled, incorporating some ledger stones or of wood block or parquet, although there's a raised timber boarded pew platform in the north aisle. St Mary's has many of the characteristics associated with churches we have covered earlier. Expressly, the built form comprises a single internal space, except for a vestry, and is centred on a tall nave rising up to a clerestory, as you can see below the higher pitched roof in this slide. There's a chancel to the east, north and south aisles, and a west tower accommodating a ground floor bell ringing chamber. The building dates from the late 11th century onwards, is Grade 1 listed, and lies at the heart of the village within a conservation area. Much original fabric is still in evidence, including important medieval detail. There are weekly services, although future use of the church is under review by the PCC due to a dwindling congregation. Next slide, please, Nigel. Until late 2019, the heating system consisted of high-level shortwave infrared heaters suspended from the nave roof timbers or otherwise fixed into wall tops. These heaters were installed about 40 years previously. They provided conditions that were generally tolerable in winter, albeit with parishioners often ending up with warm heads and cold feet. Ultimately, however, the heaters no longer functioned properly, were life expired and spare parts unavailable. Hence, you'll probably notice one heater being missing in this slide. Next, please, Nigel. A new heating installation was needed then, possibly alongside other measures to improve comfort and cut energy use. Could something radical be undertaken, namely insulating the walls internally when installing new heating? From a building conservation perspective, it was clear, however, that such work would be inappropriate to the character of the building and would harm its historic significance, not least its ancient lime plasterwork, 14th century cycle of wall paintings depicting episodes in the life of St. Margaret, the martyr of Antioch, and various fixtures, including a brass of a knight in full armour. Even if the walls weren't of historic significance, carbon savings from insulating the walls internally would be minimal, as a straightforward calculation for 40mm thick wood wall insulation board demonstrates. We have a total internal wall area of approximately 535 meters squared that would need insulating. This would require about 661 boards, each of which weighs 5.5 kilograms, giving us a total weight of 3,636 kilograms for the insulation. According to the inventory of carbon and energy, the IC database that Nigel's mentioned, there's 0.98 kilograms of CO2 embodied in each kilogram of wood wool, what's known as a material's carbon factor. So if we multiply the weight of the boards by 0.98, this gives the total embodied carbon for the 661 insulation boards, which is 3,563 kilograms. Allowing little for installation on top of this, we end up with a total embodied energy figure of about 4 tonnes. The Church of England's own data suggests that a small church with a floor area below 250 metres squared has a carbon footprint of 2 tonnes of carbon dioxide per year. So installation of internal wall insulation with embodied carbon of 4 tonnes makes little sense, particularly when we remember that the windows and roofs make up a high proportion of the building envelope and their insulation levels would remain unchanged. This is contrary to a common assumption that insulating old buildings is nearly always beneficial when it comes to saving the planet. The best way forward for intermittently occupied buildings, such as in our example, is not to concentrate on the fabric, but instead go for a solution that focuses particularly on the heating system and its use, because total energy consumption over 1 year is going to be very small. Next slide, please, Nigel. The PCC commissioned an option study to guide the choice of heating system from a firm of consulting engineers with historic buildings experience. They also consulted the inspecting architect and DAC heating advisor. The input received from these specialists was invaluable and narrowed the possibilities down to 3. So firstly, an oil-fired boiler with water-carrying radiators and a limited amount of underfloor heating below pews, where the timber floor finishes here were not of great age. Secondly, a heat pump with oversized radiators and again some underfloor heating. And thirdly, electric heating, including pew heaters, a localized trial of which was undertaken as shown here and was considered successful. I should stress that underfloor heating is something that the SPOB strongly opposes where it involves the loss or damage of historically important floors. And also it's generally preferable to obtain impartial advice from a building services consultant rather than go directly to a contractor or supplier who will often have a vested financial interest in the system selected. Do bear in mind as well that some grants are provided by dioceses for option/feasibility studies. And the next slide, please, Nigel. Option 3, electric heating, was eventually the one that was chosen by the parish on the recommendation of the consulting engineers. It involved electric convector heaters under the pews in the nave, supplemented with electric fan convector heaters in the aisles and vestry, and under carpet heating in the bell ringing chamber. Options 1 and 2, involving an oil-fired boiler and heat pump respectively, would have incurred high capital costs, entailed visually intrusive external enclosures, and require continuous running to maintain comfort conditions. Option 3, though, offered lower capital and maintenance costs, was highly efficient with quick response times, hence did not have to be run continuously, and was also aimed primarily to heat people rather than the large volume space with high ceilings. The heating installation itself was also far less extensive and likely to contain less embodied carbon. The data for this was not available. The main challenge with the all-electric option 3 was identifying appropriate cable routes. In the end, it was decided to run them below the woodblock flooring, as you can see here, rather than along wall tops and down columns. The underpew heating was installed in the nave prior to the pandemic and seems to have been judged effective, though it must be pointed out that the church has been used far less frequently than usual during the intervening period. The intention is to install electric fan convector heaters in the north and south aisles, along with the under carpet heating in the ringing chamber, as part of a second separate phase of work once the necessary fundraising has taken place. Next slide, please, Nigel. Other measures have also been identified. The DAC heating advisor recommended that consideration be given to installing a heavy curtain or an electric overdoor heater for draft exclusion around the west door in the ringing chamber, and the former has since been done. And provisional plans exist for a toilet and servery at the west end of the big 19th century north aisle. The servery would double up as a small meeting room, which could be heated separately from the main body of the church. Thanks, Nigel. Back to you.
Thank you, Douglas. At the end of the day, as decision makers, we've got to find a balance. And we need to find a way of comparing this embodied impact. Now, Douglas came up with a figure of about 4,000 kilograms of CO2 for the notional internal wall insulation at St Mary's. It's not just the wall insulation. I ought to stress you've got to then put a finished surface on top of that, be it some form of plasterboard and all the fixing. And if you thought about the total impact, you might say it was in the region of 7 tons. Working out on the same sort of basis that we talked earlier, let's say that gave us a 3,000 kilowatt hours per annum saving. Well, that would translate to about 540 kilograms of CO2 on a gas heated system, and a bit less on an air source heat pump based on a coefficient of performance, a seasonal performance factor rather, of 2.5. Manufacturers tell you you're going to get a coefficient of performance of 4 out of your system, walk away. The data does not tell you that. The recorded data, the empirical data. Over a long period, you can see that the amount that is saving starts to get something like the embodied impact. And these figures are purely notional, but I just wanted you to see how they actually start to relate to each other. Over a very long period with a gas boiler, you probably are going to come up with a net saving. with insulation, and bear in mind that there are other impacts from carrying out insulation work. It's a bit more nuanced if you go for an electrical form of heating, because the electrical grid is decarbonising and decarbonising impressively rapidly. I had little faith that they would achieve what they have done, largely with the introduction of an enormous amount of wind power, and especially offshore. So this comes back to the kind of problem that we're up against of retrofit causing embodied emissions now, while the saving is some years into the future. So, if we're trying to achieve a carbon neutrality or a net zero something or other by 2030 or even 2050, then it starts to make quite a lot of retrofit measures look unattractive. And you might say, well, actually, we'll get smart with the heating systems, and that's just what they did at the example that Douglas gave us. Having said that, there is, as Carrig correctly concluded, no one-stop shop for comparing embodied emissions with savings in use. The STBA recognised this and has started to work on a tool. We expect to complete it at a very early stage next year. So as you go into this tool, you'll be able to put in what kind of building it is, what it's made from, not forgetting, of course, it's going to be non-domestic as well as domestic. The examples you've got there look domestic, but that's your way into the tool. You'll get these choices, but once you've put in those choices and put in a particular measure, it'll then estimate the embodied carbon in that measure. It'll then estimate the carbon savings from the measure, and you'll get a choice of timescale over which to make that comparison. As we saw in the previous slide, the timescale makes quite a bit of difference to the result. And most of the people on this call are caring for buildings which have an incredibly long timescale built into them. They're already many hundreds of years old in most cases, and your perspective is different. So we do need to be looking long term, and we have the ability and the responsibility to look long term. So we'll of course let Catherine know when this tool is launched, and she can then share it with you all. Just before we conclude, I want to make you aware of one or two resources which are out there at the moment. There's a very useful publication from the Royal Institute of Chartered Surveyors, Whole Life Carbon Assessment for the Built Environment. Developing a client brief was published by the UK Green Building Council, and that really tells you how to build in embodied carbon into your purchasing, into your procurement decisions, and putting things out to tender. So that's a useful document as well. There's a very, very good website, which I use a lot in my kind of general sustainable building work, called GreenSpec. And that will tell you not only what the embodied energy and I think also embodied carbon is in different materials, it will also tell you what their other impacts are, and gives you some very useful basic information about an enormous variety of building materials. And the person who's behind that is also behind the database that STBA are just producing, the new tool. The Alliance for Sustainable Building Products has got some great guidance on embodied energy, and is really a great place to start if you're looking at any kind of fabric improvements, because it will really guide you towards the most appropriate materials, A, for the environment, and B, for old buildings, because as Douglas pointed out, they need to be moisture open, they need to be able to breathe. And there is indeed the link for the ICE database itself. So I'll commend all those further resources to you. And I think that's probably enough for us for the moment, and really want to hand it over to you to pick our brains with questions.
Brilliant. Thank you very much, Nigel and Douglas. You clearly have a very thorough understanding of a really can be quite a little bit of a complicated subject. Do you mind stopping sharing your screen just so that people can see us now? Thank you. So everyone listening, if you've got any questions, if you find the Q&A and pop them in there. There's been one question so far, and I've typed an answer to it, which was about where we can find grants for feasibility studies and options studies for improving the efficiency of buildings. So I've put in there a link through to the national funding list and through to the church energy audit programme. Nigel and Douglas, I don't know if you have anything to add to that in terms of routes to funding.
I would just add that
there's no simple answer to it.
No, with I mean, grants, as we all know, are becoming so scarce now, few and far between. But certainly with the Church and Wendon Zambo, not for that particular heating feasibility study that I mentioned, but for the toilet and servery, they had a feasibility study done for that, and the Diocese of Chelmsford did contribute towards the cost of that. So it was from the diocese.
So there's no, oh, there we go. Just as I was about to say there were no questions, one popped in. So we've got a question from Diana. What are the pros and cons of replacing a gas boiler with an electric one that will use existing pipework and radiators?
And I can have a crack at that if you like. A heat pump prefers delivering heat at a lower temperature than a gas boiler. If you're using the existing distribution network, you'll be running it at the same temperature as a gas boiler, and therefore the heat pump won't run terribly efficiently, I'm afraid. So you're likely to be using quite a lot more electricity in that case. It will, I think, cost you around double what the gas is costing you to run. There is an embodied impact to the heat pump itself. If it's a regularly used building, as Douglas explained, that probably will have an impact, therefore make the embodied impact of the heat pump relatively small, so you don't need to worry about too much about it in embodied energy terms, but it is going to cost you a lot more to run. That would be my first thought. So you've got anything to add to that, Douglas?
The question actually isn't asking about a heat pump. I don't think it's asking about an electric boiler. So replacing a gas.
An electric boiler, I beg your pardon.
Boiler with an electric boiler.
Okay, even more expensive to run because that's electrical resistance heating. So
well, you've got a real trade-off, haven't you? Because the price per unit of electricity is currently much more expensive than gas, although hopefully at some point in the future the government will start to even that up and move some of the green tariffs which are placed on electricity and move those over to gas. But from a carbon point of view, if you can get away from fossil fuels and move on to electric, because the grid is decarbonising, electricity is becoming cleaner and cleaner and cleaner.
Well, at the moment, electricity, at the moment, electricity is higher carbon per kilowatt hour than gas.
Oh, they're about the same now, aren't they? And then electricity is going down as the grid decarbonises. So over time, electricity is becoming much cleaner. Douglas, did you have anything you wanted to add on that one?
I don't think so, thanks. Other than that, the point Nigel mentioned about radiators. Yeah, we do get cases where people think, oh, wonderful, just put in some kind of heat pump. But yeah, if you're not taking into consideration that you need oversized radiators, you know, that can be a big omission that you come to later down the line, which I have seen in one or two cases actually.
Yeah, and I think it points to a wider principle, doesn't it, that the more of the existing system that can be retained, the less embodied carbon the change is going to have.
Exactly.
So we have a question from Shirley. It says, our lighting system, which involves some halogen units installed 14 years ago, is starting to fail. We'd like to replace them with a comparable system in LED. Can we get impartial advice on what units would suit? The only option seemed to be to go unguided to a supplier and then getting an installer or going to a contractor. So I guess there's a wider question about where people should look to for advice on these kind of projects.
Shall I come in on that one, Catherine? Just to say that at the SBB, we have a wonderful grant from Historic England to run it's free impartial technical advice line, which is weekday mornings 9:30 a.m. to 12:30 p.m. And over that advice line, we normally try to give people 2 or 3 names in each case of specialists, so they can then approach those people and see if they're suitable for their particular project. But we do have the names of some consulting engineers that could exactly as needed in this case, offer independent advice on types of lighting system. That number is 020 7456 0916. So that's 020 7456 0916, and it's weekday mornings.
Very useful. Also, of course, some dioceses will have a lighting advisor to the DAC, won't they, who might be able to give some support. And if you get a church energy audit, either through the national programme I've put a link to in the chat, or through your, if your diocese has a programme, then your church energy audit may be able to give you some guidance. Anything else to add on that, Nigel?
No, I think that's very comprehensive.
Very good. What's the next question says? Is the operational carbon table that you showed in section 7, why was the annual saving for biomass at 0? And can you talk more generally about biomass for heating church premises?
Sure. Well, biomass is effectively 0 carbon in operation as long as the biomass is sustainably sourced. In other words, that where it's being harvested from is being replanted. And that's thanks to the carbon cycle. I mean, in fact, if some aspects of the biomass are being removed and permanently sequestered, i.e. you're taking some timber out of the trees and the biomass for fuel is coming from timber waste, then the cycle remains actually carbon negative. So biomass heating is really a very, very low or 0 carbon option. And it's far better than anything else available at the moment in carbon terms. There's very little genuinely low carbon gas available from digesters. It's around, but biogas is, and bio-LPG is starting to come along on stream as well, I should add. But biomass, one of the hats I wear is I inspect, on behalf of Ofgem, the energy market regulator, I inspect biomass installations. I do see an awful lot of them. Haven't seen many in churches, but where there is a high demand for heat, I've seen a lot of chicken farms, and a lot of old buildings will go for biomass because it's better. It is a boiler. It's better suited to delivering the kind of high temperatures that old buildings require, because you can't actually insulate them in many cases for the reasons we've discussed. So biomass is a very good option. It can be extremely low maintenance as well. And depending on what form of biomass you use, and something like pellet or wood chip is effectively automated in just in the same way as gas is. You do need to allow for fuel deliveries now and again.
I'll just pop the link in the chat to our brief guide to biomass boilers, in case that's of use to you. The next question is from Jemima that says, thank you for your clear worked example. Are the estimated percentages of savings of different interventions available, or are these guesstimates for each bill?
They're guesstimates. I'm just trying to illustrate a point. When I was a consultant, and especially working on things like the low carbon buildings program, I was constantly asked to calculate savings. There are so many complete estimations involved, and when people start telling you it's sort of the payback period is 3.57 years, you can't go to even one decimal place on these things, because there are a really broad brush assumptions involved all over the place, and all buildings are different. They've got different proportions of windows. They'll have different proportions of heat losses through each thermal element, as Douglas explained, depending on the shape and size of the building. So no, it really is rule of thumb. Modeling doesn't help us an awful lot on this one, because it's so imprecise. It gives the impression of precision, but I'm afraid that's a false impression.
And how, other than your years of experience, is there some way that people can get a sense of what those sensible guesstimates are if they're looking at sorry, I'm trying to prevent my cat walking in from the right hand side. You might see a tail. Is there a way that people can get a sense of what sensible guesstimates are if they're looking around their church and they're thinking, right, what percentage might I be losing through the windows?
Well, I mean, I would always go for common sense. So a wall is a better insulator than a single glazed window, and let's say it was a stained glass window. Always allow something for air leakage. So let's say 20% of the heat loss from a building is going to be air leakage, and then you might say 30% for the walls, and that leaves 25% for the roof and 25% for the windows. But if it's a very tall building and a very narrow building, then it's going to have much, a relatively small roof area. So you can start to then reduce the losses through the roof. If it's got tons and tons of windows, you can up that. But if you start from some kind of basic rule of thumb of something like 20, 30, 25, 25, and then make adjustments according to the built form, I think you've got half a chance.
There's a question from Jeffrey who's asking you to look into your crystal ball. You might well say this is one that none of us are quite qualified to answer. Will the gas grid be decarbonised in line with the government's 2050 target? If we remove the gas infrastructure from our churches now, might we regret that later? That is a crystal ball question.
Forgive me for carrying on talking, Douglas. Just tell me to shut up if you want to say something. I think leaving the infrastructure in is really, really important for a number of reasons. One is the advent of hybrid heat pumps. So as the grid decarbonises, heat pumps will become more attractive, even though at the moment it's still going to be very expensive. But if you're talking about an air source heat pump, I'm afraid the temperature of the heat source, i.e. the air, is lousy in midwinter, i.e. when heat demand is highest. So a hybrid heat pump will switch over to the gas element of the boiler at that point when the air temperature drops, let's say, below 7 degrees centigrade. And it will instead use the heat pump during what we call the shoulder months of spring and autumn, where the air temperature is higher, where the heat source is better. So you'll end up with a net saving, and you'll probably end up better off in carbon terms and as well by using a hybrid. And there is a proposal, as you rightly say, to reduce the carbon intensity of the gas grid. Some boilers, in fact, all boilers put in since about the last 15 years, I think, can accept up to about 20% hydrogen without any further change needing to be made to the boiler. There are already some boilers being produced now which are hydrogen ready. So if we do get excess hydrogen production, for example, from in the summer when you got PV everywhere, that sometimes produces more energy than the grid can use. So if we use that energy to produce hydrogen, that gets around the storage problem. And batteries don't deal with it. Potential energy doesn't deal with it. Heat storage doesn't deal with it. But hydrogen doesn't go off until you put a match to it. So that's a good way of storing energy. So hydrogen may have a role to play. So I wouldn't suggest getting rid of that infrastructure for the time being.
And I think, looking at the time, this is going to be our last question, and I think it's an excellent one to finish on, from Henry, that says, do you have 2 to 3 rules of thumb, priorities related to embodied carbon that ordinary folk in PCCs could incorporate early on in the process of a refurb or reordering? So what are the rules of thumb that you would ask people to have in mind?
I've got an initial one, which would be, don't undertake big projects for small savings. I think that's I would suggest as a key takeaway. Yeah. And I think also I would say that it's important to look at things holistically. That's not to say that, like in the example I gave, actually, when in December you can't phase them because obviously you normally have funding constraints, but you do need to start off taking that impartial look, like I said, not rely on a particular contractual supplier who's trying to flog a certain type of system, but to take that overview and then you can prioritize and pick things off one by one and approach it that way. Those would be some initial thoughts from me.
Presumably what we mentioned earlier as well about the more of the existing system that you can retain and reuse, you're saving on embodied carbon. Is there a rule of thumb about materials as well? I think a lot of natural materials, wool and wood and hemp products tend to have a much lower embodied carbon, don't they, than cements and metals. And yep. Is there a rule of thumb people can use there?
I mean, certainly I would start by looking at those, and I would start certainly if you are into doing sort of serious U-value calculation and so forth to actually take good reliable base data, and by doing that opens up the options more for the breathable, the vapor open solutions. I would say so. I think, yes, certainly not only are they good in terms of of their embodied carbon, often compared to alternatives, but they're obviously better for the fabric and of the building and the health of the occupants in the long run.
Nigel, any other rules of thumb from you to add?
If you're spending money, you're causing emissions. So spend less, emit less.
There we go. That's us. It's 1 o'clock. I'm conscious there are 2 questions we haven't answered. One of them, Michael, is about heat pumps. And I really suggest you watch the video of our heat pumps webinar, because I suspect that'll give you all the answers to your question you need. And the other, I'm sorry, we've just run out of time. Thank you so much, Douglas. Thank you so much, Nigel. You're clearly bringing such a wealth of knowledge and experience to this topic. Thank you to everyone that's joined us today. As I said at the beginning, I will send around the slides and the links from the chat, and also we're running this webinar on 2 more occasions. So if you've got to the end and wish that a colleague was here, please let them know that they can book onto one of the future dates or watch the video once it's up on our website. Thank you everybody for joining us, and I'll just bring us to a close. Goodbye.